Hello students, welcome to the physics classroom. Today we are going to learn about potential energy. Potential energy. Potential energy can be thought of as stored energy. You think about this as the energy stored energy. We can look at some examples of potential energy or where potential energy is manifested. Let's look at a stretched or compressed spring. When you stretch or compress a spring, then the spring has the potential to do work. So a stretched is or compressed spring has potential to do work, has the potential to do work. I can draw that quickly maybe here. So we have an idea of how a compressed spring look like. This is a wall and that's the spring here. And imagine you have a mass connected to the spring. The spring can do work to the mass because you have compressed it by tossing it out. So right now, the spring has stored energy. Or this is compressed. This is a compressed, but also you can have a stretched spring. I usually draw my surface like that by now, you know. And this is the stretched spring. Well, try my best. This is a stretched spring. Now, if you release it, you see the mass will be pulled towards that direction. And this one will pull the mass towards this direction. So either way, whether I compress or I stretch the spring has the ability to do work on the mass, you know. So we call that this is a potential energy, stored energy in the spring. We can also have an example of a drawn ball. I'm talking about this ball. This is a ball, and this is that string that goes like that, and you have your arrow. This is my arrow here, and when you do this, when you draw a ball and arrow, you have actually potential energy in the ball string system. So what we have here, we see that a drawn ball has potential to do work. It has potential to do work on the arrow, That is the potential energy of the ball and string. Okay, this is stored energy. We can also think about another example would be a stretched rubber band. Think about a stretched rubber band. The stretched rubber band has potential to do work. Potential to do work. All right. And also when we have chemicals like molecules, atoms together, you know, forming like an explosive material or a piece of dynamite. Think about an explosive material. Or if not the explosive material, think about the apple, the food we eat, the fuel. That one also has stored energy, and the stored energy is chemical energy. So chemical energy is a form of potential energy, chemical energy. All right, so if you have a chemical reaction can do work. Yeah, we know that. A chemical reaction can do work. Think about an explosion. So a chemical reaction can do work. All right, okay. So what about gravity? If you think about an elevated object, so an elevated object, I'm thinking about elevating a boulder or maybe a crate. I like to talk about a crate. It's easy, or a bowling ball. An elevated object has the potential to do work also, has the potential to do work. You know what happens when you elevate or when you lift up a boulder to a certain height? When you release it, it goes down and it does work on the ground. Or it can actually push things, it can dent things, or maybe think about a pile driver. When it falls down, it can actually do work to objects that it hit. Okay, so an elevated object has the potential to do work. All right. Now, in general, we have types of potential energy, types of potential energy. Okay, so we have number one is, as you can see, we talked about elastic. So elastic potential energy, for example, a ball, a rubber band, a spring, compressed spring, those are elastic potential energy examples. Chemical energy, we have seen examples of the Apple fuel, explosive materials, that's chemical potential energy. In the last example, we talked about elevated object. That one is for gravitational potential energy. So gravitational. Okay, so we have elastic, chemical, and gravitational potential energy. All of these relates to energy, stored energy, and it has to do with the position of an object with respect to some reference level. Okay, now we are going to focus much on gravitational potential energy in this class or in this discussion. We are going to focus on gravitational potential energy. Gravitational, I'll just put PE, meaning potential energy. Now, gravitational potential energy is actually the work done against gravity in lifting an object. So we see that gravitational potential energy is actually equal to, is the same as the work done against gravity in lifting an object. So this is the work done against gravity in lifting an object. Okay, so work done to lift an object. Think about if you have an object sitting on the surface, like here, and object has mass m, and you'd like to take it to a certain height, maybe h, some height h. Now, as you do so, if you are doing this, maybe lifting the mass at constant velocity, at least you need a gravitational force. In other words, you need, I should say, you need a force equal to gravitational pull in order to move the box at a constant velocity upward to do the work. So what we are saying here is that the work done in lifting the object, work done in lifting the object will be the applied force, the force you put in, and then we multiply by the height. That will be the distance, so height here. And since you need at least the force due to gravity in order to be able to successfully lift the object, right now we have, for force due to gravity, and the balance is support force here. In order for you to move the box upward, at least the force must be a little bit greater than Fg, and then later on you can go back to about the same force Fg, and you can move the box at a constant velocity upward. So basically what we are trying to say is that you need actually the force equal to mg to be able to lift the object to some height. All right, okay, initially a little bit larger than Fg, you are going to lift the object. Then once you balance Fs and Fg, you can keep on moving the box to some height. So for that reason, we are justified to say that the force you are exerting on the box to do the work is just the gravitational force, and you multiply that by the height. Now, the gravitational force is mg, and the height is h. Now we are saying that this is the force acting upward. It's no longer like a gravity, it's the applied force. It's the applied force that you are acting on the box, so it's positive, it's upward in the height. It's also, I mean, you are going up, displacement is up, so positive work. This will be positive work. In this case, the work done against gravity is just mgh. That's what we are saying. That's the work done against gravity. So the potential energy, gravitational potential energy, is given by, in summary, what we are saying here is that gravitational potential energy can be calculated by multiplying the mass of the object, acceleration due to gravity, times height. This is the formula we are going to use a lot in our discussions whenever we want to calculate gravitational potential energy. For example, if you have the mass of an object as 2 kilograms and you have the height you have raised it to 4 meters and 4 meters. So what will be potential energy? From now onwards, we just say potential energy, but it's actually gravitational. So you're going to go ahead and say potential energy is mgh. That will be 2 kilograms times, we use 10 meters per second squared, and the times height is 4 meters. That will give you 80. 2 times 10, 20 times 4, 80, and the units are the same. The units of energy and the units of work are the same. So we're going to put J here. So 80. All right, so that's 80 joules. I would like you to take note of the following points, some notes about potential energy. That will be very crucial for you to understand potential energy. Now, when an object falls, the work done by gravity is equal to the loss in potential energy. So take note that when an object falls, the work done by gravity, is actually equal to the loss in potential energy. Is equal to loss in potential energy. I'm thinking about this situation here. We have our 1 kilogram object, 1 kilogram, and it falls through some distance here, 2 meters, and the work done by gravity, in this case, work done by gravity will just be equal to mg, that's gravitational force, times distance is the height, so mg times the height. So in this case, we're going to have 1 kilograms times 10 meters per second squared times the height is 2 meters. So this gives you the work done of 20 joules. Now, what is the loss in potential energy? The loss in potential energy, we can find it by looking at how potential energy has changed. So the change in potential energy is equal to the final potential energy minus initial potential energy. And the final potential energy when the ball is somewhere there, here is 0. Initial potential energy is just mgh, and that gives us, the mgh is similar to here. So that gives us minus 20 joules. So the change in potential energy is negative because we are losing energy. In other words, we are starting with a higher potential energy, ending up with a lower potential energy, and our result in the change in potential energy will be negative. So there's a loss of potential energy of 20 joules. So there is a loss of potential energy. So that is to say, potential energy is lost. Potential energy is lost. So this means that it means what? It means 20 joules of potential energy is lost. Okay, because you have allowed the mass to fall through a distance of 2 meters. So you have lost this one, but it is also equal to the work done by the work done by gravity. The work done by gravity is force times distance. The answer is 20 joules, and the loss in energy is 20 joules. So we are saying that when an object falls, the work done by gravity is equal to the loss of potential energy. That's note number 1. We are going to take note also on another point. So point number 2 about the gravitational potential energy is that gravitational potential energy depends on height. Or we should say potential energy is relative to some reference level. So we see that potential energy is relative to what? To some reference level, to some reference level. That's what we are seeing. In other ways, we have to specify which one is 0 energy and this one is what we're looking for. For example, I might have my height here and the object is here. Then I'll say, what is the potential energy at this point with respect to this point here? Right? Or I can say, okay, maybe my surface is here and the object is here. I can ask what is the potential energy here with respect to somewhere here. Okay, so it's with respect, it has to be with some reference level. So here I can say with respect to this level, what is the potential energy? Someone who is calculating potential energy here with respect to this level, they're going to find a different answer. Or maybe I can have even bigger height, and then I ask what is the potential energy here. Potential energy here is how much for this object with respect to this point. So reference level, here is our reference level, and here is our reference level. Likewise, here is our reference. All right, so it is actually with reference something. When you say potential energy is equal to mgh, this height, you have to see how the problem is like. Where should we start from? All right, so it's with respect to some reference level. All right, another point about potential energy, point number 3, is that potential energy does not depend on the path. So potential energy does not depend on the path, Okay, taken. So I'm assuming that I would like to raise an object. Maybe from here, I want to take the object all the way to some height, maybe here. Okay. So when I do that, I have also another option. Maybe I might want to take a different route. This is my surface here, and the object is here. Then maybe I might want to cruise through different line. I end up with the same height here. Yeah, so this is a different route. So you can push your object like that, or you can go straight like that. This height here, this height is the same as this height here. So as long as you end up with the same height, this is a reference level. As long as you end up with the same height, then the potential energy is the same, because it just depends on the height. It depends on the height. It doesn't depend on anything. So this is a frictionless. Okay, frictionless, and this is a frictionless also. Frictionless. Okay. You see, so the path here is frictionless, and the path here, as long as both paths are frictionless, the work done to elevate the border to some height is the same, doesn't matter. Even if you take maybe multiple steps, maybe the different situation now. Let's say you take your ball from here, you take it through this distance, and then you do that, and then you do that, you do that, you do that. Eventually, you go to the same height, you know. Now, when you do that, you rest be assured that the end result is the same. The height here is what matters. It doesn't matter if you take this route, you go this way, you go up, you go here. I mean, the most important thing is, where do you end up with? Do you end up with the same height? If the answer is yes, then as long as all these paths are frictionless, no friction here, no friction on this surface, no friction on these surfaces here, no friction here, no friction on this or the surface. As long as friction is ignored here, you are going to see that the work that you do is independent on the path. So potential energy does not depend on the path that you take to elevate the object. All right, so that's very, very important. All right, so let's see. Well, anyway, looks like this is the end of our discussion regarding potential energy. So remember, the potential energy is something that you can think about as a stored energy. Stored energy. We gave an example of a stretched or compressed spring. It is said to have potential, or sorry, it is said to have the potential to do work. If you stretch a spring or compress spring, a drawn bow has potential to do work on the arrow, as you can see here. That's elastic potential energy. We have looked at chemical potential energy, and we summarize to say that stored energy can be elastic, chemical, or gravitational. And we moved on to look at gravitational potential energy. And we saw that gravitational potential energy is actually the work that you do against gravity in lifting an object. So when you compare the work, because we already know how to calculate the work, we can actually come up with a formula for gravitational potential energy. We know if I am to lift this box at a constant velocity upward, at least I need the force equal to force of gravity. This is the force I need to lift the object, and that's the height. This is the definition of work, force times distance. Now, Fg is gravitational force, but that's actually the force that I need to lift the object. The applied force has to be equal to gravitational force times h, and I happen to come up with the mg because gravitational force is mg times h, and therefore I have a formula that we can use, that the work done, this work done that is used again, I mean work done against gravity and lifting, mgh, this one is actually the potential energy. So we have a formula to calculate potential energy. From now onwards, gravitational potential energy will be given as mgh. All right. We looked at an example. If you're given 2 kilograms, height is 4 meters, what is potential energy? You just substitute the values. We use 10 here and you get your potential energy as 80 joules. And we looked at the 3 important points about potential energy, especially gravitational potential energy. The first is that when the object falls down here, the work done by gravity, that's the force of gravity times distance, the work done by gravity through this distance 2 meters here is the same as how much potential energy you lose. So we saw that when we do that, mgh is the work done by gravity. At the same time, the loss in potential energy is also mgh, as we have seen here. So that's one point about gravitational potential energy. And we looked at point number 2, which says that potential energy is always relative to some reference level. You know, you have to specify, like we looked at this example here. This example, we see that, oh, let me see. This example, we looked at this situation. We have a reference level is just this surface. And yeah, I'm asking what is the potential energy here? If you want to do that, I need to see that you are using the height here because your reference level is actually h, so you want to use this. And if I give you potential energy here problem, and I say with reference to this, that means I want you to take this height here. See here, the same level, but then height is different. So if I say, what is the potential energy here? You say, oh, okay, where is the height? With reference, okay, the reference point is here. So your height will be all of this, all of this. So that's what we mean by when you say potential energy is relative to some reference level. That's what we mean. All right. And finally, we saw that potential energy does not depend on the path that we take. You remember when you lift an object upward, we ignore air resistance, we ignore any influence of friction, right? So you just lift it up to this level. If someone had to do the same thing, lift the boulder through some height, as long as the surface here is also not obstructing the motion, no friction, no opposition to movement, then we are going to see that the same amount of work will be done here. And likewise here, as long as the surfaces here are frictionless, then you're going to do the same amount of work as here and same amount of work like here. The most important thing is that this height are the same, and therefore the work done is independent of the path. It just depends on the height. Summary, mgh. This is the key. This is the key. It's the height. Okay, it's the height, not the distance. It's the height. The height. Okay. All right. So we stop here. If you have any questions, please let me know. I'll stop here for now.